University of Sibiu in Romania. He's got degrees in physics engineering and also in system analysis and computer programming, and a PhD in atomic physics that he obtained in 1998. After the PhD, he did a 2-year postdoc in the United States at the University of Illinois at Urbana-Champaign. And currently he's working on the topic of today's talk on dynamic and static light scattering, but also he has worked in the past in time series processing, Monte Carlo simulation of stochastic systems, and also on the characterization and synthesis of nanoparticles. Well done, thanks for accepting to be the presentation today, and the floor is yours.
Thank you. So just a few words about the university, Lucian Blaga University of Sibiu. Well, Sibiu is placed in the center of Romania, actually in the southern part of Transylvania. It's a very old city. First written proofs about Sibiu are older than 2,000 years. So it used to be a small Roman city by the time. And the medieval part of the city has been beautifully restored in 2007 when it was the cultural capital of Europe along with Luxembourg. And ever since it remained a touristic city all over the year, not only in summer, with cultural life. Hardly ever there are passing a few days without any cultural event going on, and also a nightlife in small bars and so on, with jazz, live music and so on. The Lucian Blaga University is an average-sized university in Sibiu, ranked as the 16th out of 54 universities in Romania. But that ranking that was done in 2011 is kind of controversial because they gathered data, and for 3 months they looked over the data, and finally they presented the criteria together with the ranking. So it was kind of weird, mostly quantitative criteria, extensive rather than intensive. So bigger universities appeared higher in ranking. So not like a physicist would like intensive criteria, but rather extensive. And because it was controversial, it hasn't been repeated since 2011. So the last ranking is 16th. The 16 out of 54 universities that submitted themselves to that evaluation process. Now, about dynamic light scattering, I will make a brief introduction, and if I'm telling things that are already known, just kick me forward, please. Do not let me bore you with that. Then I will go through the so-called traditional procedures for dynamic light scattering, time series processing. Then I will present the artificial neural network-based procedure I've been working on during the last 2 years, and some results, also experimental results if they are interested, and a brief conclusion. Why is dynamic light scattering important? Because particles are suspended both in air and in water, and they have certain influence on environment and on human and other living beings' health. This would be a range of particle distribution in air. How can they be visible? Health effects they have. Nanoparticles, small particles have effects, while bigger particles can be handled by body's natural filters, not only one, different filters. And, well, this is a filtering procedure to remove them. Of course, this image is taken from the internet. It's not made by myself. This would be pretty much the same type of image for particle ranges in water. We see here like red blood cells cover a different small area here in this range that goes up to 1,000 nanometers to 1 micron, maybe a little bit more than that. So this would be different range of particles suspended in air. Some of them present different can endanger the health of human beings and other beings. So for certain applications, it is interesting to know exactly and fast the size of the particles. And this is a dynamic light scattering. What the dynamic light scattering is doing about particle sizing. If we go, for instance, in a little bit more details, as it has to do with particle diffusion in solvents, can be air or water or different solvents. The output is not the real diameter, like in transmission electron microscopy or scanning electron microscopy for bigger size particles, but it's so-called hydrodynamic diameter because it has to do with particle diffusion in solvent. And these are some typical biological structures because they are colored, and I took them because they are colored. Physics is typically black and white, but biological structures are colored, so they look nice. And just to have an idea about the real size and the hydrodynamic diameter. What would be a typical experimental setup? Well, another few words I want to say is that I started some years ago working on this dynamic light scattering more or less from a set desire of setting up a very simple dynamic light scattering experimental setup almost from scratch. That means from what I can typically find in a student lab, maybe undergraduate student lab. So very simple parts put together, still working, because this method is actually absolute method, not a relative method. So the question was, can I make from very simple parts working a dynamic light scattering setup and a simple data processing procedure, and that can still give good results? And somehow I started more or less like a joke, and then I started working on that. Typically would have a laser, helium neon laser. It's better because the red light is less absorbed by biological structures. If you are thinking, we are thinking of using it on biological samples as well. Can be a laser diode, but depending on the power supply, it can introduce some noise. A lens, a sample, that is a suspension with particles, nanoparticles or micron-sized particles. Then we can select the scattering angle, put another lens, a detector, and historically an autocorrelator was used, but now computers, any laptop can do the computation fast enough that the hardware part like an autocorrelator is no longer necessary to be used. So it can be simply a data acquisition system and a PC. This would be a typical far field interference. This is recorded with a webcam. Well, actually, charge coupled device webcam with optical system removed. So it's actually the interference directly on the conversion device. We see fluctuations on it. And if you place a detector in any area of it, it will record a time series. So actually, particles undergo a chaotic motion, Brownian motion, plus can be sedimentation. If the particles are bigger, then sedimentation can play a role in that. Each particle is absorbing light, and it's emitting secondary waves. And the Hines-Fresnel principle, if we apply it, each wavelet, waves are emitted by each particle in any direction and in any place in space, they interfere. If we place a detector, we see the interference in that place. And as the particles are moving, we have seen the kind of boiling speckles aspect, random succession of maxima and minima. That time series can be analyzed as it contains information in each location of the far field. Information is contained about all the particles that were in the active area. So information about that can be somehow unraveled by processing the time series. Qualitatively, if we have bigger particles, they move slowly. If we have small particles, they move faster. So we expect that bigger particles produce fluctuations with smaller frequencies, while smaller particles impose faster fluctuations in the time series. And now that would be qualitatively what dynamic light scattering is. We'll go a little bit further in the so-called traditional procedures for dynamic light scattering, time series processing. And there are actually more approaches. If we are considering mono dispersed particles, that means not a wide distribution, we can use a power spectrum approach or the autocorrelation approach. And there are also methods, I will talk about them a little bit later, real brief, that process the time series and even try to find the particle size distribution or identify several groups of particles suspended in that carrier fluid. So first of all, the power spectrum approach. That's bad. Empty. Well, I don't know. Half hour ago it worked perfect. I don't know what happened. So if we have time series, maybe I should switch to that PDF. That should have the images frozen in it. While I'm opening it. Yeah, something. I had formal presentations in Windows, but on Monday morning, the Windows partition, the Windows I had just cracked, and I couldn't start it again. I also have a Linux partition on my laptop, but the Windows 10 just kept that partition with the data block, so I worked on a flash drive, and that mismatch caused that, and somehow the Windows was so intimidated of the so many Linux machines here that it collapsed, finally collapsed, and it didn't start again. So we have a time series here. Basically, we do a Fourier transform. If we have a continuous function, this relation makes a link between the time domain to the frequency domain. And if we have a time series, which actually have a set of data, not a continuous function, but we can use a fast Fourier transform algorithm, and we can compute the frequency spectrum. And for such this is a sequence of a time series, we find such a spectrum. Doesn't look very nice, it's not that smooth, but we can fit a line through those data. The flow chart would be to take the sample. Dynamic light scattering means recording a time series from a stochastic system. Then the fast Fourier transform algorithm converts it to the frequency spectrum. We do fit the expected shape of that spectrum, which is a Lorentzian line to it. And from the parameters, we can find the average size of the particles that are suspended. The experimental setup is very simple. A laser diode. We use a glass cuvette. It's much better than a plastic, but the plastic works as well. We use typically 90 degrees, but depending on the maximum data acquisition rate, we can select different angles. We lose precision, but it's actually adjusting all those physical experimental parameters to find the range to match the range of the particles we desire to analyze. Then from that detector, the signal goes to a PC, and on some experiments, I could even use the sound card of the PC for data acquisition. Sounds surprising, but any PC or laptop has a sound card. It's better not to use it on a laptop, because if it's burned, it's definitely burned. But in a desktop, it can be easily removed or put another one. They are made in big number, very big number, and the quality has been constantly improved, and the price of the sound card is very low simply because they are made in such a big number. And it's actually a good quality data acquisition system that can go up to 44 kilohertz, providing that we do not want to measure continuous signal or very small frequencies in it. Then it has that filter on the input and it kind of filtering the very, very small frequency signal. The Lorentzian line looks actually like this line we see here. If we plot it in a double logarithmic scale, it has a plateau and then it has coming down part. And if we do the intersection of those two, we find what is called the rollover point. And the rollover point is related actually to the size of the particles that are suspended. There are a lot of experimental concerns. The speckle size, which we have seen on that moving part, speckle size should match the detector size. Otherwise, different coefficients should be applied, and then it's altering the data if we do not do it correctly. But that can be physically adjusted. Then the distance between the sample and the detector has to be adjusted. The bigger the distance, the smaller is the detector compared to the speckle size, but the smaller is the intensity, and then we might need an amplifier that also introduces some noise and complicates things. We are departing from a very simple experimental setup. Then, of course, the maximum acquisition frequency has to be adjusted, because if we have a maximum frequency in the spectrum, we should use at least data acquisition frequencies that should be at least double of that maximum frequency. Otherwise, we have this aliasing phenomenon. For instance, if we measure with a frequency like that, and we measure this data, and we have a big frequency signal, it can actually be recorded as a smaller frequency. That will increase the small frequency part of the spectrum and can lead to alterated results. That means particles have a bigger diameter than the actual diameter if the small frequency part is increased. So if these experimental concerns are being addressed, then we also have to take care about the concentration of the sample. This is again an image taken from the internet. Depending on the size, we see here are particles around 1 micron, and looking through those cuvettes, we see printed paper behind, and this would be, exactly the same particles suspended, and these are the diameters that are the output of this dynamic light scattering procedure. We see that there is a plateau of concentration range, and then for very big concentrations, we have diameter predicted, which is much smaller than the actual diameter. If we are looking at nanometer size particles, for instance, 36 nanometer size particles, we can use smaller concentrations, and the plateau is a little bit more extended. But roughly, we can see by eye, we should be able to see through that cuvette. Now, what means that Lorentzian fit? We fit this function, which has two free parameters, A0 and A1. F is the frequency. We fit that through the least squares procedure to this power spectrum, and we get the continuous red line, which is the best fit. A0 is required in order to scale the Lorentzian line to match the plateau, and A1 parameter is the parameter of interest, and it is related to the radius of the suspended particles. Once we find A1, we find the radius. This is K, which is sometimes also noted as Q. It's a scattering vector. And theta is a scattering angle. So this is the procedure. Find directly in 2 steps, find the radius. What we need is the refractive index of the solvent, the viscosity of the solvent, temperature, wavelengths, scattering angle to measure them precisely. And we do not need a calibration because it's an absolute method. Once we take care of all those experimental details, we get the diameter. There are also some fitting artifacts depending on the power spectrum. The intensity frequency spectrum is also called power spectrum. We can have results that are not accurate if these two parameters are orders of magnitude different. Then the smaller one can get to the smallest step we can select, and then the fitting stops. But then I did a normalization of that frequency spectrum, of the power spectrum, and that is possible because we are only interested in A1 parameters, which is related to the turnover point, and then scaling that makes, for instance, the biggest values is made to be, for instance, 1 or maybe 10, depending on the range, makes both parameters be in the same magnitude, and then we get a good fit. So a brief overview, a brief conclusion of that is quite simple. The procedure is quite simple. Filtering is simple because once we have the frequency spectrum, we can simply cut the noise by removing that small interval with the noise. Simply remove it with the program, just read the spectrum, cut down that, write without that. So fitting will not be done on the noise. Normalization increase in procedures. There are only two parameters. That makes the least squares fit to be quite reproducible or almost always reproducible. It has a disadvantage that it's not quite a real-time result. If we want something that would work real fast, for instance, in less than 1 second since we start measurement, this doesn't quite work because fitting by least squares involves many function computations, numerical gradient, adjustment function computations, and so on until it finds the results. So it's not quite in real time. Now, if we go further, we have the other traditional approach, the autocorrelation approach, which means that we can compute the autocorrelation of a time series. This is a mistake. I apologize. This should have been a tau here rather than t. So the autocorrelation is typically for a stochastic time series is actually an exponentially decaying function. In the real world, we find not a continuous function, but we find discrete values measured at typically the same time interval. And so we do the computation as an average. And for dynamic light scattering time series, monodispersed, typically that autocorrelation of the intensity has this shape, a constant, an exponentially decaying part, and another constant. This can be easily normalized by subtracting the B part, and then if we were careful and have chosen the size of the detector to be as close as possible to the average speckle size, then we can normalize A to 1 without mistaking anything. Then if we have this exponential decaying function, we can easily fit the parameter, which is D. Q is the scattering vector, it's all known. It's K as I wrote it just a few slides ahead. And then we find the diffusion, D is the diffusion coefficient, which is related by Einstein formula to D, the diameter of the suspended particles. The advantage is that we only have one free parameter, which makes the fit 100% reproducible. This is an example of an experimental autocorrelation function, and the red line is the fitted exponential decay on it. We notice here that the experimental autocorrelation function is not that ideal. It also has here some small maxima, which for this kind of function are produced by different frequencies and different noise that was also recorded. If we have several groups of particles, we actually see an overlap of some exponentially decaying functions like that and like that and like that. And if it is a continuous distribution, then it's pretty much an exponentially decaying function. What would be the conclusion of this time series processing? It's a difficult filtering because we have to use an active filter, which makes experimental setup to be not as simple as I started planning of. So an active filter, or there is an alternative to compute the power spectrum, so the same Fourier transform, then from the power filter the power spectrum, and then recompose the autocorrelation from the filter power spectrum. Appears to be easy. I tried, it didn't work always, so I didn't go on that way. But ignoring that, fitting is much simpler because it's only one parameter, it's much faster, it's 100% reproducible. And the advantage is that if we can go around filtering, we can get almost real-time results. There are also DLS procedures for polydispersed suspensions. I want to mention briefly the Contin, the cumulants method, and the maximum entropy. Contin procedure uses an inverse Laplace transform, which is an ill-posed problem, requires a regularization, introduces a parameter, and choosing that parameter is not fully automatic and has a big influence on the solution. So it doesn't go by itself. It pretty much can be precise, but requires a human intervention on data analysis. The maximum entropy is an enhancement of the fitting method, assigning an entropy to its solution and choosing the solution which has the maximum entropy. But all these methods have a limitation to 4 or 5 groups of particles. For each particle group, we need at least 2 parameters. For instance, if we are thinking of a Gaussian distribution, we need the maximum, the position of the maximum, and for instance, the standard deviation, so 2 parameters for each. And if we go for 5 groups of particles, then we need 10 parameters, and if we have done least squares fitting, that 10 parameters is not always reproducible. So we need different starting parameters for the fitting that would give to a chi-square which is smaller than the first time, but with totally different results. So it's not that fully automatic. But what I did was not about deriving the distribution, but working on suspensions that can be approximated as pretty much monodispersed suspensions. Now, the other approach would be an artificial neural network-based procedure. We cut down the part with the Fourier transform, with the frequency spectrum, with fitting Lorentzian, or with fitting the autocorrelation, and we simply replace it with computing the autocorrelation function, no filtering, using an artificial neural network trained for that. That will give information about the particle size. Now, probably you are well aware of artificial neural networks, and I shouldn't be in more detail, so should I stay on that? I really have no idea. An artificial neural network consists of more so-called artificial neurons and layers of artificial neurons interconnected. And if we take one such artificial neuron, it actually has inputs from all the other neurons from the previous layer that are input with different weights. Also adds a bias that scales the signal, has this signal A, then has a transfer function that produces an output, and this output is also sent to all the neurons in the next layer. that's a typical artificial neural network for fitting. Can be, it must have one input layer, it also must have an output layer, and it should have at least a hidden layer. Now another nice image from the biological structure. It's called a neuron. It has dendrites, it has an axon that has terminals, and these terminals connect to the dendrites of other neurons. If we have an analogy, we have here inputs from other neurons. Weights are put in the sum, added with a bias, transfer function is applied, then we have an output that goes again to the other neurons in the next layer, hidden layer, or maybe the outer layer. It's based on the so-called universal approximation theorem that was published by Sibenko in 1989, and it was proved that using the so-called sigmoid functions, which are actually hyperbolic tangent functions, as a transfer function, such a structure can be found, such a structure with enough neurons that can approximate as precisely as we need a certain continuous function. And Hornig in 1991 proved that such an approximation can be achieved not only with sigmoid functions as transfer functions, but with almost any transfer function. So what we actually need is a set of elementary processing units called the neurons, connections between them. Then we need a set of function or for neural data processing. That means we need the propagation function, an activation function, and an output function that actually transforms into an output of the network. It's a measurable signal. Then, of course, it's a learning strategy that can iteratively adjust the weights and the biases in such a way that the output is optimized and produces an approximation. For instance, if you want to approximate a function, produces the approximation with the precision we want. So learning strategy is also something that is adjusted. That would be a typical 3 layers neurons, an input layer, then has neurons in the first layer, and the output of them is transferred to all the other neurons in the second layer with different weights. Added the bias transfer function is applied. We get outputs from each neuron, which are again input for the third layer with other weights and biases. And iteratively, during that so-called learning process, that is those weights and biases, sometimes biases are slowly adjusted to produce a desired output. That would be a training procedure to find the arrays of weights and biases that minimizes the so-called error difference between the target and the output. Training can be unsupervised. A neural network deducts correct answers by analyzing all the input data without any proper response. There are certain applications, bioinformatics, data and pattern mining, medical imaging, computer vision. I haven't been working on these kind of things. And it's also the supervised learning or training when we have a set of input data and a set of targets, and those are used during the training process to produce those weights and biases. It's a backpropagation. The supervised method was a backpropagation with gradient descent. As I mentioned, is calculating the error, computing different sets of weights and biases to produce the minimum error, and that procedure is repeated until we can manually stop it on when it reached a certain precision. It's important to choose the right number of samples and to choose properly the so-called architecture of the neural network, the number of input layer. I mean, the size of the input layer, it depends on the data we input, the size of, the number of the hidden layer is crucial, because if it's too small, so-called fitting is not precise. If we put more and more neurons, we can get accurate result for the training set, but then the network is unable to predict a good result for an unknown set. It's called overfitting for the artificial neural networks. So actually, we need the minimum number of neurons that predicts the result with the precision we intend. Of course, we have to represent the problem correctly and to choose the proper training algorithm and strategy. Now we go closer to the artificial neural network for dynamic light scattering. We see a time series or a sequence of a time series, and we can ask ourselves, what can we use as an input for an artificial neural network? I will simply call it neural network. Can it be the time series? Hardly, because it can have tens of thousands of data, and different time series can look completely different, but can have the same program power spectrum or can have the same autocorrelation. So I tried both directions, the power spectrum and the autocorrelation as input for the neural network. Now, power spectrum as an input. We see here a power spectrum as computed on a recorded time signal. We see here the frequency. In Europe, the power grid works at 50 hertz. So it's hardly ever, if we record in a lab something, even if we use very good screening, we can still see the 50 hertz and harmonics, 100 hertz, 150, 200, and so on. And these are quite strong frequencies in the spectrum. We see this is a double logarithmic scale. If we are filtering that simply in the power spectrum, we just cut down, for instance, the 50 hertz and a quarter of a hertz smaller and a quarter of a hertz bigger, so half hertz center or 50 hertz on the harmonics. We simply cut down all that noise. We have a rather clean, yet experimental power spectrum. We know that the expected power spectrum should be described by the Lorentzian line. And for instance, for recording at 30 degrees with a sampling rate of 12 kilohertz, I plotted here power spectrum for several diameters from 100 to 600 nanometers. We see that as the diameter increases, the power spectrum gets more closer to a straight line, and the turnover point is harder and harder to be caught. So for that small angle and small frequency, we have a limitation for 350 nanometers. So it would be a neural network trained for nanometer size particles. The input cannot be the power spectrum as it is, so I did some averages. I did averages on it. For instance, I did averages on 100 intervals, and that would mean that we have actually 100 data in the power spectrum. It's essential that we use the same filtering procedure for the computed power spectrum, ideal one with the Lorentzian line, and for the experimental data. We should use the same and averages on the same interval, because we want the input to the neural network to be frequencies to be the intensity in the power spectrum for precisely the same frequencies. Then we need big sets of data, and by the time I did that in 2016, I saw that 2,200 sets of data for 2,200 diameters was a big set of training data for a neural network. It was quite a small neural network. It had 20 neurons in the hidden layer. The training algorithm was Levenberg-Marquardt. 15% of the data used for validation, 15% for testing, and 70% of the data for training. It worked pretty fast, 153 iterations, and it reached the correlation coefficient of 1, lasted 7.5 minutes on quite a modest laptop. These are the results on simulated time series. For small diameters, the neural network predicts a smaller diameter, and this would be the relative error considering fitting with the power spectrum fitting as a reference. Then it decreased, and then we see that for bigger diameters, the neural network overestimates the diameter. If we plot this diameter, the straight line would be the predicted diameters, and the red dots are the predicted diameters, and the blue line are actually the diameters that was used in simulating the data. We see that it is pretty good, but not perfect. And I had this type of neural network and neural network processing had it published in 2017. Then the second one, which is a little bit better, is to use the autocorrelation as input. Why should we use that? Because we do not need filtering as a time series. We can actually train the neural network with noise. And that was one of the nice things I found. And also, the averaging is not related to the size of the frequency spectrum. The longer the time series, the more precise the autocorrelation is. So it's less sensitive to the length of the recorded time series. And of course, we need a minimum size, minimum amount of data to do the autocorrelation. And we still have this problem, noise removal, because we didn't use an active filter. At this point, in order to get better results, we have to train the neural network not with simply computed autocorrelation functions. I tried that, as I did in the previous version, with computed Lorentzian lines. We have seen the big errors, 11%, 9%. I've done it the same here. It didn't work well. Then I thought of solving this challenge, how to produce the outcome of a stochastic system using a deterministic procedure, actually a sum of harmonic functions. So I start working on that, computing the time series, not the autocorrelation directly, but generating time series. And the question is, what would be the amplitude and the frequencies and the initial phase of this superposition of sinuses, for instance, or harmonic functions that could produce a realistic time series as the output of that suspension undergoing a Brownian motion and light scattered by, and coherent light scattered by that suspension. I went back to that theoretically expected frequency spectrum, and the amplitude of each frequency is actually the square root of that S function, which is a Lorentzian line, the expected frequency. Random numbers should be used for the initial phases, otherwise all the sinuses sum up at the beginning and we get something a very big increase at the beginning and then oscillation. So if we use random number for initial phases, I also tried it for the frequencies to be random numbers in a certain interval. It didn't work so well. But in this way, if we generate, for instance, for the same diameter, different time series, they will be different. And if we compute the diameters will be slightly different from each other, not ideal, for instance, 20 nanometers. Then this is the final solution. Phases initially randomly, using random numbers, the frequencies were generated in this interval. This would be the half of the data acquisition system expected to be used in experimental time series. And also, I thought of investigating the effect of the number of frequencies that is used to generate that time series, and then of the length of the time series. So I took, for instance, 2 at 14 data, the same frequency, 12 kilohertz, and then I tried different frequencies to generate the time series, going with powers of 2 up to the 13 power, because that is the number of frequencies that is an output. If we have 2 at n, power of n data, the fast Fourier transform will get 2 at n minus 1 number of frequencies. And I did that. I also did it for 2 diameters, and these are the results. For instance, the blue line is for a small number of frequencies, 513, so actually 2 at the power of n plus 1. We see that it doesn't look very nice. It's not quite exponentially decaying. It also has oscillations if we go farther on. Then as we increase the number of frequencies, we get the curves overlapping and getting the nice expected form, exponentially decaying form. So if we plot the errors, the relative errors, considering fitting the autocorrelation as a reference, we see that for small particles, the errors are small, but for bigger particles, we see very big errors if we use a small number of frequencies. And we see that the best, a zero error or close to zero error we get if we use 2 at the power n minus 1 plus 1 frequencies. So many frequencies, bigger computation time, but we cannot find a shortcut to that. If we go further on to see the effect of the length of the time series, keeping the result, the same result, that means if we have 2 at n power lengths, we need to use 2 at n minus 1 plus 1 frequencies. I have done different simulations for the same 20 nanometers and 1,200 nanometers, which are close to the limits of the range I trained the network for. And we have seen the same pattern. Small particles lead to smaller errors, but bigger particles have very big errors for short time series, and the error are going to 0 for longer time series. What can be the explanation? Bigger particles. Bigger particles have smaller frequencies in the power spectrum. If we use a small number or a short time series, the smaller part, the part of smaller frequencies, for instance, if you do a Fourier transform, is not accurately represented. So a conclusion in generating this would be, conclusion would be we need at least 2 at the 13 number of data points, and if for n we use 2 at the power, this is a simple n minus 1, simple n minus 1, so not 2 but just 1. Then we have to solve the noise problem also, experimental noise. So in those time series I added noise, just looking and filtering the data and separating the noise. I figured out that the 50 hertz and harmonics, the amplitude is decreasing exponentially as we increase the frequency. And then I generated a separate time series with the noise, with this relation. Why is this coefficient, trial and error, this work better? Now theoretical 5 minutes, okay. Then also random noise was added to those time series. So generated using harmonic functions, added the 50 Hertz harmonics, then random noise amplitude also decreased exponentially with the frequency. And I got time series which were pretty good resemblance with the exponentially time series. Then computed, the autocorrelation is computed for each time series and placed in columns in an array. And for each set, the target would be the diameter, not the ideal diameter, but the diameter that was computing using the fitting autocorrelation function fitting on it. And these are the autocorrelation of simulated time series. We see that for smaller particles, 100 nanometers, we see the blue line and we see that pattern, noise pattern added and distorting that. And that distortion is less visible as diameter increases. There could have been another alternative. In 2008, I did a computer simulation of the Brownian motion, and by moving each particle independently by small steps, and then coherent light scattered by that suspension was used to produce either a time series or an image or that boiling speckled recording that I've showed you at the beginning, but that would be awfully time consuming. And for instance, for 1 second, generating 1 second, it would be maybe 14 or 15 hours of computing for a time series of 1 second. So going to 60,000 sets of data would be quite impossible on the computation platform I have. So I use the first 350 data in autocorrelation, 26 neurons in the hidden layer, 1 output layer, which is average diameter. Training stopped after 58 iterations, took 38 minutes on this time better laptop, and results on simulated data. The range was from 0 to 1,200, doing the relative error between the diameter that is fit by the neural network minus diameter that, I mean, this is a fit and this is a neural network divided times 100. Result is in percent. We see that in the small area we see relative big errors, in the big area very small errors. If we zoom in a small range of diameters, we see that over 40 we have errors smaller than 3%. So we can conclude that this artificial neural network can predict accurately the results for diameters in the range 40 to 1,200 nanometers. Some experimental results, real brief. We can use a simple procedure like sedimentation to make sure that we have in the beam area particles that are smaller than a certain amount, certain diameter. If we see the velocity of the falling ball, it's proportional to the square of the radius. So after time t, from the beginning, for such distance L between the upper part and the beam, we have only particles that have a velocity smaller than v, therefore a diameter smaller than d. That's very useful if we have particles that have a known density, then we are for sure that we do not have particles that are bigger than that in that. So we can pretty much, with a little patience, we can pretty much adjust in such a way that we have particles, for instance, smaller than 150 nanometers. No bigger particle is crucial because light scattering, the intensity of light scattered by one particle is proportional to the 6th power of the diameter. So a few bigger particles actually distort the interference field. And we can do a measurement as time passes. We can do a measurement, record time series, and process those time series both by autocorrelation fitting and by the neural network procedure, and we see the blue dots are the fitting, least square fitting, and the red dots are the neural network diameters. They are pretty close. The errors are very small. If we draw a line with those two, the correlation coefficient is quite big. We also see, if we go back, that the errors increase as time passes. That means that the diameter decreases, and we are moving towards that area with relatively bigger errors in the neural network predicted diameters. But it's much faster. Other type of results are, for instance, milk proteins aggregation. So milk proteins were produced by, well, separated by centrifugation. It was also calcium lactate was added and induced aggregation, and we measure the variation of the diameter during aggregation. This is the time scale. Here we see that the same pattern. The neural network predicted diameters are a little bit bigger, but the result is much faster. I did this type of experiments. The first one is pretty much monodispersed particles, while the second one, it's not quite single-sized. During protein aggregation, you can have different sizes, and this was done to test how robust these predictions are. Box plot with errors is here, of course. The average is different, but we see that as the polydispersity of the particles suspended increases, the error increases, and the values are more spread around that. How fast is that procedure? For instance, for 30 time series, that is recording that works in batch mode, for 30 time series, the least squares fit lasted for 0.13 seconds, while the artificial neural network was much faster, roughly 6,700 times faster. It's hard to say that that's correct because it depends on the input parameters. If we fit in a batch mode, we have to assign some input parameters to certain values. If it happens that they are close to the values of the time series, that fitting is faster, otherwise it's bigger. If we choose different start parameters for the fitting, we might get a different time, but roughly, I would say 5,000 to 7,000 times faster, that neural network procedure. As a brief conclusion, what I think it was interesting was that using perfectly deterministic functions like harmonic functions, the output of a purely stochastic system could be simulated accurately, I mean realistic. Then a very simple neural network with one hidden layer of 26 neurons was enough to compute the average diameter. Possible directions would be to design that have not the output average size, but the distribution, but still work to be done on that, on defining the set of input data and training procedure, and of course the output. Also, DLS can be done in air as carrying fluid. Very few people have done it. It's harder to be done. It requires bigger frequencies. The particle density is much smaller, so amplification is required, and there are also complications. And maybe a generalized conclusion that in the output of a stochastic system, a certain pattern can be identified, then artificial neural network can be trained to identify the system's characteristics which are related to that pattern in one or another. Some acknowledgements. These are two internal grants that I have used, and a small amount of money that are financed by the university can be used exclusively for small parts, or purchasing small parts or whatever you need to complete a study. Also, Sibiu Mihai Ray is my PhD student. He will defend his thesis on October 12th. he brought the artificial neural networks to my attention. We started working. He went on a different direction. He did Python neural networks and scanned tools that scans automatically for optimum neural networks, structures, and so on. And his work will be presented there. I didn't talk about his work, but anyway, fruitful discussions with him were helpful in pushing me on this artificial neural network direction. And thank you.
Any questions?
As far as I understood, you use only the fluctuations in a single speckle.
In a single speckle.
Have you tried to use the information from many of them, or is it
Yeah.
too difficult to
Yeah,
in static like scattering?
Yes,
it's
it's
image.
yes, it's static light scattering.
Combine the two things.
Yes, I've done that. I've done the static light scattering. Typically, people use up to 20 detectors, different angles, but I put pretty close the charge coupled device. So I actually had a ribbon of hundreds of detectors. Each cell becomes a detector, and fitting that, it is called the phase function that describes anisotropy of light. I did that, and I could identify the size of the particle. But that's static light scattering, averaging on succession of frames and so on.
But this is worse than
It's different. It's different. This type of dynamic light scattering can be done for fast processes. I didn't talk about that. I've done it, but without artificial neural networks. For instance, to assess the dynamics of nanoparticle aggregation. If, for instance, iron oxide nanoparticles are diluted in water, not in salts or anything, they aggregate pretty fast. And I did those type of measurements. But then you need a long time series, and you slice it down and do dynamic light scattering on each slice, and you find the dynamics of the variation of the diameter in time. But it was older work. I haven't talked about that now. And that is static light scattering. I have also done that some time ago. Yeah. That can work with artificial neural networks as well. I mean, fitting the phase function. Actually, the integral of the phase function over the size of a cell on the conversion matrix. It has a certain size and has to be integrated over it. And that will be.
Other questions?
Other than particle size, dynamic light scattering can show this information on, for instance, particle velocities.
Yes, it has been done. There is a technique called seeding a fluid with light scattering particles, and then bigger particles where Brownian motion is less important or less sensitive, and then it's used for measuring the fluid flow velocity. In a fluid, it has to be transparent or half transparent. It is also that is used on in biology. They are using, it's called the laser. It's laser speckle contrast analysis. It's used to image blood flow on the back of the eye, or they used it to image blood flow in rat brains, but not yet in human brain, because on those rats and mice they removed the skin and they polished the skull, so it was very small layer of bone, so the laser could penetrate and they could image the blood flow, but not on humans, living humans yet. It is used, but then it's related to speckle contrast analysis more than dynamic light scattering.
If not, Dan is going to stay here this week, so tomorrow and Friday. We're going to keep this in the guest office. So, let's thank Dan.
Thank you.